Learning objectives. In this chapter, the user would learn the following in detail. Introduction, operating systems, multi-programmed batched system, time-storing systems, parallel and distributed systems, real-time systems. Computer system structures, I/O structure, storage hierarchy, hardware, protection, general system architecture. Services, user interface services, graphics and multimedia services, messaging and collaboration, network basics, web services. Operating system structures, system components, operating system service, system calls, system programs, system structure, system design and implementation, system generation, virtual machines and hypervisor. Introduction. A computer without software is basically a useless lump of metal, whereas with its software, a computer can store, process, and retrieve information, play music and video, send email, etc. Computer software can be divided roughly into two kinds. System programs, which manage the operation of the computer itself. Application programs, which perform the actual work the user wants. An amazing aspect of operating systems is how they vary in accomplishing these tasks. Mainframe operating systems are designed primarily to optimize utilization of hardware. Personal computer, PC operating systems support complex games, business applications, and everything in between. Operating systems for mobile computers provide an environment in which a user can easily interface with the computer to execute programs. Thus, some operating systems are designed to be convenient, others to be efficient, and others to be some combination of the two. Computer system structures. Computer system operation. I/O devices and the CPU can execute concurrently. Each device controller is in charge of a particular device type. Each device controller has a local buffer. CPU moves data from to main memory to from local buffers. I/O is done from the device to local buffer of controller. Memory controller is used to ensure orderly access to shared memory, so its function is to synchronize access to the shared memory. Device controller informs CPU that it has finished its operation by causing an interrupt. Computer system architecture, as shown. A modern general-purpose computer system consists of one or more CPUs and a number of device controllers connected through a common bus that provides access to shared memory. The figure below displays a modern computer system. Each device controller is in charge of a specific type of device, for example, disk drives, audio devices, or video displays. The CPU and the device controllers can execute in parallel, competing for memory cycles. To ensure orderly access to the shared memory, a memory controller synchronizes access to the memory. For a computer to start running, for instance, when it is powered up or rebooted, it needs to have an initial program to run. This initial program or bootstrap program tends to be simple. Typically, it is stored within the computer hardware in read-only memory (ROM) or electrically erasable programmable read-only memory (EEPROM), known by the general term firmware. It initializes all aspects of the system, from CPU registers to device controllers to memory contents. The bootstrap program must know how to load the operating system and how to start executing that system. To accomplish this goal, the bootstrap program must locate the operating system kernel and load it into memory. Once the kernel is loaded and executing, it can start providing services to the system and its users. Some services are provided outside the kernel by system programs that are loaded into memory at boot time to become system processes or system daemons that run the entire time the kernel is running. On Unix, the first system process is init and it starts many other daemons. Once this phase is complete, the system is fully booted and the system waits for some event to occur. The occurrence of an event is usually signaled by an interrupt from either the hardware or the software. Hardware may trigger an interrupt at any time by sending a signal to the CPU, usually by way of the system bus. Software may trigger an interrupt by executing a special operation called a system call, also called a monitor call. When the CPU is interrupted, it stops what it is doing and immediately transfers execution to a fixed location. The fixed location usually contains the starting address where the service routine for the interrupt is located. The interrupt service routine executes. On completion, the CPU resumes the interrupted computation. A timeline of this operation is shown in the figure below. Interrupt timeline for a single process doing output. Interrupts are an important part of a computer architecture. Each computer design has its own interrupt mechanism, but several functions are common. The interrupt must transfer control to the appropriate interrupt service routine. The straightforward method for handling this transfer would be to invoke a generic routine to examine the interrupt information. The routine in turn would call the interrupt-specific handler. However, interrupts must be handled quickly. Since only a predefined number of interrupts is possible, a table of pointers to interrupt routines can be used instead to provide the necessary speed. The interrupt routine is called indirectly through the table with no intermediate routine needed. Generally, the table of pointers is stored in low memory, the first 100 or so locations. These locations hold the addresses of the interrupt service routines for the various devices. This array or interrupt vector of addresses is then indexed by a unique device number given with the interrupt request to provide the address of the interrupt service routine for the interrupting device. Operating systems as different as Windows and Unix dispatch interrupts in this manner. The interrupt architecture must also save the address of the interrupted instruction. Many old designs simply stored the interrupt address in a fixed location or in a location indexed by the device number. More recent architectures store the return address on the system stack. If the return routine needs to modify the processor state, for instance by modifying register values, it must explicitly save the current state and then restore that state before returning. After the interrupt is serviced, the saved return address is loaded into the program counter and the interrupted computation resumes as though the interrupt had not occurred. General system architecture. A computer system can be organized in a number of different ways, which we can categorize roughly according to the number of general-purpose processors used. Single processor systems. Until recently, most computer systems used a single processor. On a single processor system, there is one main CPU capable of executing a general-purpose instruction set, including instructions from user processors. Almost all single processor systems have other special-purpose processors as well. They may come in the form of device-specific processors such as disk, keyboard, and graphics controllers, or on mainframes, they may come in the form of more general-purpose processors such as I/O processors that move data rapidly among the components of the system. All of these special-purpose processors run a limited instruction set and do not run user processes. Sometimes they are managed by the operating system in that the operating system sends them information about their next task and monitors their status. For example, a disk controller microprocessor receives a sequence of requests from the main CPU and implements its own disk queue and scheduling algorithm. This arrangement relieves the main CPU of the overhead of disk scheduling. PCs contain a microprocessor in the keyboard to convert the keystrokes into codes to be sent to the CPU. In other systems or circumstances, special-purpose processors are low-level components built into the hardware. The operating system cannot communicate with these processes. They do their jobs autonomously. The use of special-purpose microprocessors is common and does not turn a single-processor system into a multiprocessor. If there is only one general-purpose CPU, then the system is a single-processor system. Multiprocessor systems. Within the past several years, multiprocessor systems, also known as parallel systems or multi-core systems, have begun to dominate the landscape of computing. Such systems have two or more processors in close communication, sharing the computer bus and sometimes the clock, memory, and peripheral devices. Multiprocessor systems first appeared prominently in servers and have since migrated to desktop and laptop systems. Recently, multiple processors have appeared on mobile devices such as smartphones and tablet computers. Multiprocessor systems have three main advantages. 1. Increased throughput. By increasing the number of processors, we expect to get more work done in less time. The speed-up ratio with n processors is not n, however, rather it is less than n. When multiple processors cooperate on a task, a certain amount of overhead is incurred in keeping all the parts working correctly. This overhead, plus contention for shared resources, lowers the expected gain from additional processes. Similarly, n programmers working closely together do not produce n times the amount of work a single programmer would produce. 2. Economy of scale. Multiprocessor systems can cost less than equivalent multi-single processor systems because they can share peripherals, mass storage, and power supplies. If several programs operate on the same set of data, it is cheaper to store those data on one disk and to have all the processors share them than to have many computers with local disks and many copies of the data. 3. Increased reliability. If functions can be distributed properly among several processes, then the failure of one processor will not halt the system, only slow it down. If we have 10 processors and one fails, then each of the remaining 9 processors can pick up a share of the work of the failed processor. Thus, the entire system runs only 10% slower rather than failing altogether. Increased reliability of a computer system is crucial in many applications. The ability to continue providing service proportional to the level of surviving hardware is called graceful degradation. Some systems go beyond graceful degradation and are called fault-tolerant because they can suffer a failure of any single component and still continue operation. Fault tolerance requires a mechanism to allow the failure to be detected, diagnosed, and, if possible, corrected. The HP non-stop, formerly Tandem system, uses both hardware and software duplication to ensure continued operation despite faults. The system consists of multiple pairs of CPUs working in lockstep. Both processes in the pair execute each instruction and compare the results. If the results differ, then one CPU of the pair is at fault and both are halted. The process that was being executed is then moved to another pair of CPUs and the instruction that failed is restarted. This solution is expensive since it involves special hardware and considerable hardware duplication. It is important to note that while multi-core systems are multiprocessor systems, not all multiprocessor systems are multi-core. In our coverage of multiprocessor systems throughout this text, unless we state otherwise, we generally use the more contemporary term multi-core, which excludes some multiprocessor systems. In the figure below, we show a dual-core design with 2 cores on the same chip. In this design, each core has its own register set as well as its own local cache. Other designs might use a shared cache or a combination of local and shared caches. Aside from architectural considerations, such as cache, memory, and bus contention, these multi-core CPUs appear to the operating system as N-standard processors. This characteristic puts pressure on operating system designers and application programmers to make use of those processing cores. Finally, blade servers are a relatively recent development in which multiple processor boards, I/O boards, and networking boards are placed in the same chassis. The difference between these and traditional multiprocessor systems is that each blade processor board boots independently and runs its own operating system. Some blade server boards are multiprocessor as well, which blurs the lines between types of computers. In essence, these servers consist of multiple independent multiprocessor systems. Clustered systems. Another type of multiprocessor system is a clustered system which gathers together multiple CPUs. Clustered systems differ from the multiprocessor systems in that they are composed of 2 or more individual systems or nodes joined together. Such systems are considered loosely coupled. Each node may be a single processor system or a multi-core system. We should note that the definition of clustered is not concrete. Many commercial packages wrestle to define a clustered system and why one form is better than another. The generally accepted definition is that clustered computers share storage and are closely linked via a local area network LAN or a faster interconnect such as InfiniBand. Clustering is usually used to provide high availability service, that is, service will continue even if one or more systems in the cluster fail. Generally, we obtain high availability by adding a level of redundancy in the system. A layer of cluster software runs on the cluster nodes. Each node can monitor one or more of the others over the LAN. If the monitored machine fails, the monitoring machine can take ownership of its storage and restart the applications that were running on the failed machine. The users and clients of the applications see only a brief interruption of service. Clustering can be structured asymmetrically or symmetrically. In asymmetric clustering, one machine is in hot standby mode while the other is running the applications. The hot standby host machine does nothing but monitor the active server. If the server fails, the hot standby host becomes the active server. In symmetric clustering, 2 or more hosts are running applications and are monitoring each other. This structure is obviously more efficient as it uses all of the available hardware. However, it does require that more than one application be available to run. Since a cluster consists of several computer systems connected via a network, clusters can also be used to provide high-performance computing environments. Such systems can supply significantly greater computational power than single processor or even SMP systems because they can run an application concurrently on all computers in the cluster. The application must have been written specifically to take advantage of the cluster, however. This involves a technique known as parallelization, which divides a program into separate components that run in parallel on individual computers in the cluster. Typically, these applications are designed so that once each computing node in the cluster has solved its portion of the problem, the results from all the nodes are combined into a final solution. Other forms of clusters include parallel clusters and clustering over a wide area network, WAN. Parallel clusters allow multiple hosts to access the same data on shared storage because most operating systems lack support for simultaneous data access by multiple hosts. Parallel clusters usually require the use of special versions of software and special releases of applications. For example, Oracle Real Application Cluster is a version of Oracle's database that has been designed to run on a parallel cluster. Each machine runs Oracle, and a layer of software tracks access to the shared disk. Each machine has full access to all data in the database. To provide this shared access, the system must also supply access control and locking to ensure that no conflicting operations occur. This function, commonly known as a Distributed Lock Manager (DLM), is included in some cluster technology. Cluster technology is changing rapidly. Some cluster products support dozens of systems in a cluster as well as clustered nodes that are separated by miles. Many of these improvements are made possible by storage area networks, SANs, which allow many systems to attach to a pool of storage. If the applications and their data are stored on the SAN, then the cluster software can assign the application to run on any host that is attached to the SAN. If the host fails, then any other host can take over. In a database cluster, dozens of hosts can share the same database, greatly increasing performance and reliability. The figure below depicts the general structure of a clustered system. Hardware. As computer technology has evolved and as the cost of computer hardware has dropped, computer designers have sought more and more opportunities for parallelism, usually to improve performance and, in some cases, to improve reliability. Computer software is so called in contrast to computer hardware, which encompasses the physical interconnections and devices required to store and execute or run the software. The hardware, central processing unit (CPU), the memory, the input-output, that is I/O, provides the basic computing resources for the system. Hardware may trigger an interrupt at any time by sending a signal to the CPU, usually by way of the system bus. Figure shows computer hardware and software structures. A software requires various hardware requirements. For example, Minix 3 OS requires the following hardware: PC with a Pentium or compatible processor, 16 MB or more of RAM, 200 MB of free disk space, IDE CD-ROM driver, IDE hard disk. I/O structure. Storage is only one of many types of I/O devices within a computer. A large portion of operating system code is dedicated to managing I/O, both because of its importance to the reliability and performance of a system and because of the varying nature of the devices. Next, we provide an overview of I/O. A general-purpose computer system consists of CPUs and multiple device controllers that are connected through a common bus. Each device controller is in charge of a specific type of device. Depending on the controller, more than one device may be attached. For instance, 7 or more devices can be attached to the Small Computer Systems Interface (SCSI) controller. A device controller maintains some local buffer storage and a set of special-purpose registers. The device controller is responsible for moving the data between the peripheral devices that it controls and its local buffer storage. Typically, operating systems have a device storage for each device controller. This device driver understands the device controller and provides the rest of the operating system with a uniform interface to the device. To start an I/O operation, the device driver loads the appropriate registers within the device controller. The device controller, in turn, examines the contents of these registers to determine what action to take, such as read a character from the keyboard. The controller starts the transfer of data from the device to its local buffer. Once the transfer of data is complete, the device controller informs the device driver via an interrupt that it has finished its operation. The device driver then returns control to the operating system, possibly returning the data or a pointer to the data if the operation was a read. For other operations, the device driver returns status information. This form of interrupt-driven I/O is fine for moving small amounts of data, but can produce high overhead when used for bulk data movements such as disk I/O. To solve this problem, Direct Memory Access (DMA) is used. After setting up buffers, pointers, and counters for the I/O device, the device controller transfers an entire block of data directly to or from its own buffer storage to memory with no intervention by the CPU. Only one interrupt is generated per block to tell the device driver that the operation has completed, rather than the one interrupt per byte generated for low-speed devices. While the device controller is performing these operations, the CPU is available to accomplish other work. Some high-end systems use switch rather than bus architecture. On these systems, multiple components can talk to other components concurrently rather than competing for cycles on a shared bus. In this case, DMA is even more effective. Messaging and collaboration. Messaging is a method of communication between software components or applications. A messaging system is a peer-to-peer facility. A messaging client can send messages to and receive messages from any other client. Each client connects to a messaging agent that provides facilities for creating, sending, receiving, and reading messages. Messaging enables distributed communication that is loosely coupled. A component sends a message to a destination, and the recipient can retrieve the message from the destination. However, the sender and the receiver do not have to be available at the same time in order to communicate. In fact, the sender does not need to know anything about the receiver, nor does the receiver need to know anything about the sender. The sender and the receiver need to know only what message format and what destination to use. In this respect, messaging differs from tightly coupled technologies such as remote method invocation (RMI), which require an application to know a remote application's methods. Messaging also differs from electronic mail (email), which is a method of communication between people or between software applications and people. Messaging is used for communication between software applications or software components. The Java Message Service was developed by Sun Microsystems to provide a means for Java programs to access enterprise messaging systems. Before we discuss JMS, let's take a look at enterprise messaging systems. Enterprise messaging systems, often known as Message-Oriented Middleware (MOM), provide a mechanism for integrating applications in a loosely coupled, flexible manner. They provide asynchronous delivery of data between applications on a store and forward basis. That is, the applications do not communicate directly with each other, but instead communicate with the MOM, which acts as an intermediary. The MOM provides assured delivery of messages, or at least makes its best effort, and relieves application programmers from knowing the details of remote procedure calls (RPC) and networking communications protocols. Messaging flexibility. As shown in the figure below, Application A communicates with Application B by sending a message to the MOM's Application Programming Interface (API). The MOM routes the message to Application B, which may exist on a completely different computer. The MOM handles the network communications. If the network connection is not available, the MOM will store the message until the connection becomes available and then forward it to Application B. Another aspect of flexibility is that Application B may not even be executing when Application A sends its message. The MOM will hold the message until Application B begins execution and attempts to retrieve its messages. This also prevents application A from blocking while it waits for application B to receive the message. This asynchronous communication requires applications to be designed somewhat differently than most are designed today, but it can be an extremely useful method for time-independent or parallel processing. Multi-programmed batched system. Memory layout for simple batch system. Memory layout for multi-programmed batch system. Multi-programming. Several jobs are kept in main memory at the same time, and the CPU is multiplexed among them, which require memory management and protection. The OS picks and begins to execute one job from memory. Once this job needs an I/O operation, the OS switches to another job, CPU or OS always busy. The number of jobs in memory is less than the number of jobs in disk, job pool. If several jobs are ready to be brought into memory and there is not enough room for all of them, then the system chooses jobs among them, job scheduling. If several jobs are ready to run at the same time, the system must choose among them, CPU scheduling. Having several programs in memory at the same time requires memory management. In non-multi-programmed system, CPU sits idle. In multi-programming system, CPU will never be idle. Two main disadvantages of multi-programmed batched systems. Users cannot interact with their jobs while executing. A programmer cannot modify a program as it executes to study its behavior. Network basics. Network services or services are defined here as levels of performance and function in the network. We can look at this from two perspectives, as services being offered by the network to the rest of the system, the devices, applications and users, or as sets of requirements from the network that are expected by the users, applications or devices. Levels of performance are described by the performance characteristics capacity, delay, and RMA, reliability, maintainability, and availability, whereas functions are described as security, accounting, billing, scheduling, and management, and others. Network services in most of today's networks are based on best effort, unpredictable and unreliable delivery. In addition to best effort delivery, we examine some new types of services, including high-performance, predictable, stochastic or probabilistic, and guaranteed services. These new services require some different ways of looking at networks, and you will see how to incorporate such services into your architecture and design. We also look at single-tier and multiple-tier performance in the network and show how to distinguish between them and how they relate to best effort, predictable, and guaranteed services. Network services are hierarchical, and individual service characteristics can be grouped together to form higher-level descriptions of a service as shown in the figure below. Some of the networking services are NAT, DHCP, DNS, multicasting. Network Addressing Translation. NAT is a router function where IP addresses and possibly port numbers of IT datagrams are replaced at the boundary of a private network. NAT is a method that enables hosts on private networks to communicate with hosts on the Internet. NAT is run on routers that connect private networks to the public Internet to replace the IP address port pair of an IP packet with another IP address port pair. DHCP, Dynamic Host Control Protocol. Dynamic assignment of IP addresses is desirable for several reasons. IP addresses are assigned on demand, avoid manual IP configuration, support mobility of laptops. The client broadcasts a DHCP discover message on its local physical subnet. The DHCP discover message may include some options such as network address suggestion or lease duration. Each server may respond with a DHCP offer message that includes an available network address, your IP address, and other configuration options. The servers record the address as offered to the client to prevent the same address being offered to other clients in the event of further DHCP discover messages being received before the first client has completed its configuration. If the client receives one or more DHCP offer messages from one or more servers, the client chooses one based on the configuration parameters offered and broadcasts a DHCP request message that includes the server identifier option to indicate which message it has selected and the requested IP address option taken from your IP address in the selected offer. In the event that no offers are received, if the client has knowledge of a previous network address, the client may reuse that address if its lease is still valid until the lease expires. The servers receive the DHCP request broadcast from the client. Those servers not selected by the DHCP request message use the message as notification that the client has declined that server's offer. The server selected in the DHCP request message commits the binding for the client to persistent storage and responds with a DHCPACK message containing the configuration parameters for the requesting client. The combination of client hardware and assigned network address constitute a unique identifier for the client's lease and are used by both the client and server to identify a lease referred to in any DHCP messages. The Your IP address field in the DHCPACK messages is filled in with the selected network address. DHCP interaction simplified. Operating system service. User interface. Almost all operating systems have a user interface, UI. This interface can take several forms. One is a command line interface, CLI, which uses text commands and a method for entering them, say a keyboard for typing in commands in a specific format with specific options. Another is a batch interface in which commands and directives to control those commands are entered into files and those files are executed. Most commonly, a graphical user interface GUI is used. Here, the interface is a window system with a pointing device to direct input-output, choose from menus and make selections and a keyboard to enter text. Some systems provide two or all three of these variations. Program execution. The system must be able to load a program into memory and to run that program. The program must be able to end its execution either normally or abnormally, indicating error. Input-output operations. A running program may require input-output, which may involve a file or an input-output device. For specific devices, special functions may be desired, such as recording to a CD or DVD drive or blanking a display screen. For efficiency and protection, users usually cannot control input-output devices directly. Therefore, the operating system must provide a means to do input-output. File system manipulation. The file system is of particular interest. Obviously, programs need to read and write files and directories. They also need to create and delete them by name, search for a given file, and list file information. Finally, some operating systems include permissions management to allow or deny access to files or directories based on file ownership. Many operating systems provide a variety of file systems, sometimes to allow personal choice and sometimes to provide specific features or performance characteristics. Communications. There are many circumstances in which one process needs to exchange information with another process. Such communication may occur between processes that are executing on the same computer or between processes that are executing on different computer systems tied together by a computer network. Communications may be implemented via shared memory, in which two or more processes read and write to a shared section of memory, or message passing, in which packets of information in predefined formats are moved between processes by the operating system. Error detection. The operating system needs to be detecting and correcting errors constantly. Errors may occur in the CPU and memory hardware, such as a memory error or a power failure, in input-output devices such as a parity error on disk, a connection failure on a network, or lack of paper in the printer, and in the user program. For each type of error, the operating system should take the appropriate action to ensure correct and consistent computing. Sometimes it has no choice but to halt the system. At other times, it might terminate an error-causing process or return an error code to a process for the process to detect and possibly correct. Another set of operating system functions exists not for helping the user, but rather for ensuring the efficient operation of the system itself. Systems with multiple users can gain efficiency by sharing the computer resources among the users. Resource allocation. When there are multiple users or multiple jobs running at the same time, resources must be allocated to each of them. The operating system manages many different types of resources. Some, such as CPU cycles, main memory, and file storage, may have special allocation code, whereas others, such as input-output devices, may have much more general request and release code. For instance, in determining how best to use the CPU, operating systems have CPU scheduling routines that take into account the speed of the CPU, the jobs that must be executed, the numbers of registers available, and other factors. There may also be routines to allocate printers, USB storage drives, and other peripheral devices. Accounting. We want to keep track of which users use how much and what kinds of computer resources. This record keeping may be used for accounting so that users can be billed, or simply for accumulating usage statistics. Usage statistics may be a valuable tool for researchers who wish to reconfigure the system to improve computing services. Protection and security. The owners of information stored in a multi-user or networked computer system may want to control use of that information. When several separate processes execute concurrently, it should not be possible for one process to interfere with the others or with the operating system itself. Protection involves ensuring that all access to system resources is controlled. Security of the system from outsiders is also important. Such security starts with requiring each user to authenticate himself or herself to the system, usually by means of a password, to gain access to system resources. It extends to defending external input-output devices, including network adapters, from invalid access attempts, and to recording all such connections for detection of break-ins. If a system is to be protected and secure, Precautions must be instituted throughout it. A chain is only as strong as its weakest link. Operating system structure. An operating system provides an environment for the execution of programs. It provides certain services to programs and to the users of those programs. The specific services provided, of course, differ from one operating system to another, but we can identify common classes. These operating system services are provided for the convenience of the programmer to make the programming task easier. The figure below shows one view of the various operating system services and how they interrelate. One set of operating system services provides functions that are helpful to the user. Operating system. The most fundamental system program is the operating system, whose job is to control all the computer's resources and provide a base upon which the application programs can be written. Operating system, or shortly called OS, primarily provides services for running applications on a computer system. An operating system acts as an intermediary between the user of a computer and the computer hardware. The above diagram depicts computer hardware and software with their interface. At the bottom is the hardware. The lowest level contains physical devices consisting of integrated circuit chips, wires, power supplies, cathode ray tubes, and similar physical devices. In microarchitecture level, the physical devices are grouped together to form functional units. It contains some registers internal to the CPU, central processing unit, and a data path containing an arithmetic logic unit, ALU. The machine language typically has between 50 to 300 instructions, mostly for moving data around the machine, doing arithmetic, and comparing values. In this level, the input-output devices are controlled by loading values into special device registers. Next is system programs. The operating system is to hide all this complexity and give the programmer a more convenient set of instructions to work with. On top of the operating system is the rest of the system software, that is, command interpreter, shell, window systems, compilers, editors, and similar application-independent programs. On top is the application programs. These programs are purchased or written by the users to solve their particular problems such as word processing, spreadsheets, engineering calculations, or storing information in a database. The operating system is that portion of the software that runs in kernel mode or supervisor mode. Functions of operating system. Various functions of operating system are resource utilization, resource allocation, process control and management, file management, communication, information maintenance, device management. User view. The primary consideration is always the convenience. It should be easy to use an application. In launching an application, it helps to have an icon which gives a clue which application it is. We have seen some helpful clues for launching a browser, email, or even a document preparation application. In other words, the human-computer interface which helps to identify an application and its launch is very useful. This hides a lot of details of the more elementary instructions that help in selecting the application. System view. However, when it comes to the viewpoint of a system, the OS needs to ensure that all the system users and applications get to use the facilities that they need. OS needs to ensure that system resources are utilized efficiently. For instance, There may be many service requests on a web server. Each user request need to be serviced. Similarly, there may be many programs residing in the main memory. The system need to determine which programs are active and which need to await some form of input or output. Those that need to wait can be suspended temporarily from engaging the processor. Operational view. Let's briefly look at the underlying principle of operation of a computer system. Current systems are based on the von Neumann principle. This principle states that a program is initially stored in memory and executed by fetching an instruction at a time. The basic cycle of operation is: fetch an instruction, fetch; interpret the instruction, decode; execute the instruction, execute. Three elements of an OS. User interface, the part of the OS that you interface with. Kernel, the core of the OS, interacts with the BIOS at one end and the UI at the other end. File management system, organizes and manages files. The evolution. It would be worthwhile to trace some developments that have happened in the last 4 to 5 decades. In the 60s, the common form of computing facility was a mainframe computer system. The mainframe computer system would be normally housed in a computer center with a controlled environment, which was usually an air-conditioned area with a clean room-like facility. The users used to bring in a deck of punched cards which encoded the list of program instructions. The mode of operation was as follows. User would prepare a program as a deck of punched cards. The header cards in the deck were the job control cards, which would indicate which compiler was to be used, like Fortran, COBOL compilers. The deck of cards would be handed in to an operator who would collect such jobs from various users. The operators would invariably group the submitted jobs as Fortran jobs, COBOL jobs, etc. In addition, these were classified as long jobs that required considerable processing time or short jobs which required a short and limited computational time. Each set of jobs was considered as a batch and the processing would be done for a batch. Like for instance, there may be a batch of short Fortran jobs. The output for each job would be separated and turned over to users in a collection area. Limitations. No interactivity. Users had no direct control. At any one time, only one program would engage the processor. This meant that processor would be idle most of the time as processor speeds were orders of magnitude higher than the input or output or even memory units. Poor utilization of the processor. The systems that utilize the CPU and the memory better and with multiple users connected to the systems evolved over a period of time as shown in the table below. In the decade of 70s, the basic mode of operation was altered and system designers contemplated having more than one program resident in the memory. This clearly meant that when one program is awaiting completion of an input or output, another program could, in fact, engage the CPU. Late 60s and early 70s storing multiple executables at the same time in the main memory is called multiprogramming. Multiprogramming, as shown. With multiple executables residing in the main memory, the immediate consideration is we now need a policy to allocate memory and processor time to the resident programs. It is obvious that by utilizing the processor for another process, when a process is engaged in input or output, the processor utilization and, therefore, its output are higher. Overall, the multi-programming leads to higher throughput for this reason. While multi-programming did lead to enhanced throughput of a system, the systems still essentially operated in batch processing mode. In the decade of 80s. In the late 70s and early part of the decade of 80s, the system designers offered some interactivity with each user having a capability to access system. This is the period when the time-shared systems came on the scene. Basically, the idea is to give every user an illusion that all the system resources were available to him as his program executed. To strengthen this illusion, a clever way was devised by which each user was allocated a slide of time to engage the processor. During the allocated time slice, a user's program would be executed. Now imagine if the next turn for the same program comes quickly enough, the user would have an illusion that the system was continuously available to his task. Time-shared systems clearly require several design considerations. These include the following: how many programs may reside in the main memory to allow and also sustain time sharing? What should be the time slice allocated to process each program? How would one protect a user's program and data from being overwritten by another user's program? Basically, the design trends that were clearly evident during the decade of 1970 to 80 were: achieve as much overlapping as may be feasible between I/O and processing. Bulk storage on disks clearly witnessed a phenomenal growth. This also helped to implement the concept to offer an illusion of extended storage. The concept of virtual storage came into the vogue. The virtual storage essentially utilizes these disks to offer enhanced addressable space. The fact that only that part of a program that is currently active need to be in the main memory also meant that multi-programming could support many more programs. In fact, this could be further enhanced as follows. 1. Only required active parts of the programs could be swapped in from disks. 2. Suspended programs could be swapped out. This means that a large number of users can access the system. This was to satisfy the notion that computing facility be brought to a user as opposed to the notion that the user go to the compute. The fact that a facility is brought to a user gives the notion of a utility or a service in its true sense. In fact, the PC truly reflects the notion of a computing utility. It is regarded now as a personal productivity tool. It was in early 1970s, Bell Laboratory scientists came up with the now well-known OS, Unix. Also, as the microcomputers came on scene in 1980s as a forerunner to current DOS, was a system called CP/M. The decade of 1980s saw many advances with the promise of networked systems. The project forms the basis to several modern developments. The client-server paradigm was indeed a major fallout. The users could have a common server to the so-called X terminals. The X Windows also provided many widgets to support convenient human-computer interfaces. Using X Windows, it is possible to create multiple windows. In fact, each of the windows offers a virtual terminal. In other words, it is possible to think about each of these windows as a front-end terminal connection. So it is possible to launch different applications from each of the windows. This is what you experience on modern-day PC, which also support such an operating environment. CP/M-based computer, as shown. On the microcomputer front, the development was aimed at relieving the processor from handling input-output responsibilities. The I/O processing was primarily handled by two mechanisms: BIOS, graphics cards to drive the display. The processor now was relieved from regulating the I/O. The advent of 1990s. The computer networking topologies like star, ring, and general graphs, as shown in the figure, were being experimented with. Protocols for communication amongst computers evolved. In particular, the TCP by IP suites of network protocols were implemented. The growth in the networking area also resulted in giving users a capability to establish communication between computers. It was now possible to connect to a remote computer using a Telnet protocol. It was also possible to get a file stored in a remote location using a file transfer (FTP) protocol. All such services are broadly called network services. Let's now briefly explore where the OS appears in the context of the software and application. Parallel and distributed system. Parallel systems. A parallel system is one that seeks to improve performance through parallel implementation of various operations such as loading data, building indexes, and evaluating queries. Multiprocessor systems with more than one CPU is close communication. Tightly coupled system processes share memory and a clock. Communication usually takes place through the shared memory. As shown, parallel system. Advantages of parallel system, multiprocessor systems. Increased throughput, number of processes that are completed per time unit, economical for large jobs, no need to make copies of data and distribute it among several processes, faster for large jobs, divide the work on all processes, increased reliability, fault tolerant. For example, if we have 10 processes working together on a job and one processor failed, then the remaining 9 processes must pick up a share of the work of the failed processor. Thus, the entire system is still working but slower by 10%. Therefore, multiprocessor systems are reliable. Distributed systems. A distributed system is a collection of processes that do not share memory or a clock. Instead, each node has its own local memory. A general structure of a distributed system is shown below. The nodes communicate with one another through various networks such as high-speed buses and the Internet. Distribute the computation among several physical processes. Loosely coupled system involves connecting 2 or more independent computer systems via communication link. So each processor has its own OS and local memory. Processes communicate with one another through various communications lines, message passing, such as high-speed buses or telephone lines. The distributed system may vary in size and function. These processes are referred to by a number of names such as processors, sites, machines, and hosts, depending on the context in which they are mentioned. We mainly use site to indicate the location of a machine and node to refer to a specific system at a site. Distributed systems depend on networking for their functionality. Networks vary by the protocols used, the distances between nodes, and the transport media. TCP by IP is the most common network protocol, and it provides the fundamental architecture of the Internet. Most operating systems support TCP over IP, including all general-purpose ones. Some systems support proprietary protocols to suit their needs. To an operating system, a network protocol simply needs an interface device, a network adapter, for example, with a device driver to manage it, as well as software to handle data. Reasons for building distributed systems. Resource sharing. Computation speed up. Reliability. Communication. Advantages of distributed systems. Resources sharing. You can share files and printers. Computation speed up. A job can be partitioned so that each processor can do a portion concurrently. Load sharing. Reliability. If one processor failed, the rest still can function with no problem. Communications, such as electronic mail, FTP, etc. If one site fails in a distributed system, the remaining sites can potentially continue operating. Better service to the customers, reduction of the load on the host computer, reduction of delays in data processing. Protection. If a computer system has multiple users and allows the concurrent execution of multiple processes, then access to data must be regulated. For that purpose, mechanisms ensure that files, memory segments, CPU, and other resources can be operated on by only those processes that have gained proper authorization from the operating system. For example, memory addressing hardware ensures that a process can execute only within its own address space. The timer ensures that no process can gain control of the CPU without eventually relinquishing control. Device control registers are not accessible to users, so the integrity of the various peripheral devices is protected. Protection, then, is any mechanism for controlling the access of processes or users to the resources defined by a computer system. This mechanism must provide means to specify the controls to be imposed and to enforce the controls. Protection can improve reliability by detecting latent errors at the interfaces between component subsystems. Early detection of interface errors can often prevent contamination of a healthy subsystem by another subsystem that is malfunctioning. Furthermore, an unprotected resource cannot defend against use or misuse by an unauthorized or incompetent user. A protection-oriented system provides a means to distinguish between authorized and unauthorized usage. A system can have adequate protection but still be prone to failure and allow inappropriate access. Consider a user whose authentication information, her means of identifying herself to the system, is stolen. Her data could be copied or deleted even though file and memory protection are working. It is the job of security to defend a system from external and internal attacks. Such attacks spread across a huge range and include viruses and worms, denial of service attacks, which use all of a system's resources and so keep legitimate users out of that system, identifying theft, and theft of service, unauthorized use of a system. Prevention of some of these attacks is considered an operating system function on some systems, while other systems leave it to policy or additional software. Due to the alarming rise in security incidents, operating system security features represent a fast-growing area of research and implementation. Protection and security require the system to be able to distinguish among all its users. Most operating systems maintain a list of usernames and associated user identifiers, user IDs. In Windows parlance, this is a security ID, that is SID. These numerical IDs are unique, one per user. When a user logs in to the system, the authentication stage determines the appropriate user ID for the user. That user ID is associated with all of the user's processes and threads. When an ID needs to be readable by a user, it is translated back to the username via the username list. In some circumstances, we wish to distinguish among sets of users rather than individual users. For example, the owner of a file on a Unix system may be allowed to issue all operations on that file, whereas a selected set of users may be allowed only to read the file. To accomplish this, we need to define a group name and the set of users belonging to that group. Group functionality can be implemented as a system-wide list of group names and group identifiers. A user can be in one or more groups depending on operating system design decisions. The user's group IDs are also included in every associated process and thread. In the course of normal system use, the user ID and group ID for a user are sufficient. However, a user sometimes needs to escalate privileges to gain extra permissions for an activity. The user may need access to a device that is restricted, for example. Operating systems provide various methods to allow privilege escalation. On Unix, for instance, the setuid attribute on a program causes that program to run with the user ID of the owner of the file rather than the current user's ID. This process runs with its effective UID until it turns off the extra privileges or terminates. Real-time system. Real-time system is defined as a data processing system in which the time interval required to process and respond to inputs is so small that it controls the environment. Real-time processing is always online, whereas online system need not be real-time. The time taken by the system to respond to an input and display of required updated information is termed as response time. So in this method, response time is very less as compared to the online processing. Real-time systems are used when there are rigid time requirements on the operation of a processor or the flow of data, and real-time systems can be used as a control device in a dedicated application. Real-time operating system has well-defined fixed time constraints, otherwise system will fail. For example, scientific experiments, medical imaging systems, industrial control systems, weapon systems, robots, and home appliance controllers, air traffic control system, etc. Real-time systems are characterized by supplying immediate response. For example, sensors bring data to the computer. Often used as a control device in a dedicated application such as controlling scientific experiments, medical imaging systems, industrial control systems, and some display systems. Well-defined fixed time constraints. Types of real-time operating system. There are two types of real-time operating systems: hard real-time systems, soft real-time systems. Hard real-time systems. Hard real-time systems guarantee that critical tasks complete on time. In hard real-time systems, secondary storage is limited or missing with data stored in ROM. In these systems, virtual memory is almost never found. Secondary storage limited or absent, data stored in short-term memory or read-only memory, ROM. Conflicts with time-sharing systems not supported by general-purpose operating systems. Soft real-time systems. Soft real-time systems are less restrictive. Critical real-time tasks gets priority over other tasks and retains the priority until it completes. Soft real-time systems have limited utility than hard real-time systems. For example, multimedia, virtual reality, advanced scientific projects like undersea exploration and planetary rovers, etc. Limited utility in industrial control or robotics. Useful in applications, multimedia, virtual reality requiring advanced operating system features. Services. Services provided by an operating system. The following are examples of services provided by an operating system: context switching and scheduling, which allocate a process CPU time to execute its instructions; memory management, which deals with allocating memory to processes; interprocess communication, which deals with facilities to allow concurrently running processes to communicate with each other; File systems, which provide higher-level files out of low-level unstructured data on a disk. High-level I/O facilities, which free a process from the low-level details of interrupt handling. User interface services. We mentioned earlier that there are several ways for users to interface with the operating system. Here we discuss two fundamental approaches. One provides a command line interface or command interpreter that allows users to directly enter commands to be performed by the operating system. The other allows users to interface with the operating system via a graphical user interface or GUI. Command interpreters. Some operating systems include the command interpreter in the kernel. Others, such as Windows and Unix, treat the command interpreter as a special program that is running when a job is initiated or when a user first logs on interactive systems. On systems with multiple command interpreters to choose from, the interpreters are known as shells. For example, on Unix and Linux systems, a user may choose among several different shells, including the Bourne shell, BSH, C shell, CSH, Bourne Again shell, BASH, Korn shell, KSH, and others. Third-party shells and free user written shells are also available. Most shells provide similar functionality, and a user's choice of which shell to use is generally based on personal preference. Figure below shows the Bourne shell, BSH command interpreter being used on Solaris 10. The main function of the command interpreter is to get and execute the next user-specified command. Many of the commands given at this level manipulate files, create, delete, list, print, copy, execute, and so on. The MS-DOS and Unix shells operate in this way. These commands can be implemented in two general ways. In one approach, the command interpreter itself contains the code to execute the command. For example, a command to delete a file may cause the command interpreter to jump to a section of its code that sets up the parameters and makes the appropriate system call. In this case, the number of commands that can be given determines the size of the command interpreter, since each command requires its own implementing code. An alternative approach used by Unix, among other operating systems, implements most commands through system programs. In this case, the command interpreter does not understand the command in any way. It merely uses the command to identify a file to be loaded into memory and executed. Thus, the Unix command to delete a file, rmfile.txt, would search for a file called rm, load the file into memory, and execute it with the parameter file.txt. The function associated with the rm command would be defined completely by the code in the file rm. In this way, programmers can add new commands to the system easily by creating new files with the proper names. The command interpreter program, which can be small, does not have to be changed for new commands to be added. Graphics and multimedia services. A second strategy for interfacing with the operating system is through a user-friendly graphical user interface or GUI. Here, rather than entering commands directly via a command line interface, users employ a mouse-based window and a menu system characterized by a desktop metaphor. The user moves the mouse to position its pointer on images or icons on the screen, the desktop, that represent programs, files, directories, and system functions. Depending on the mouse pointer's location, clicking a button on the mouse can invoke a program, select a file or directory known as a folder, or pull down a menu that contains commands. Graphical user interfaces first appeared due in part to research taking place in the early 1970s at Xerox PARC research facility. The first GUI appeared on the Xerox Alto computer in 1973. However, graphical interfaces became more widespread with the advent of Apple Macintosh computers in the 1980s. The user interface for the Macintosh operating system, Mac OS, has undergone various changes over the years, the most significant being the adoption of the Aqua interface that appeared with Mac OS X. Microsoft's first version of Windows, version 1.0, was based on the addition of a GUI interface to the MS-DOS operating system. Later versions of the Windows have made cosmetic changes in the appearance of the GUI along with several enhancements in its functionality. Because a mouse is impractical for most mobile systems, smartphones and handheld tablet computers typically use a touchscreen interface. Here, users interact by making gestures on the touchscreen, for example, pressing and swiping fingers across the screen. Figure 2.3 illustrates the touchscreen of the Apple iPad. Whereas earlier smartphones included a physical keyboard, most smartphones now simulate a keyboard on the touchscreen. Traditionally, Unix systems have been dominated by command-line interfaces. Various GUI interfaces are available, however. These include the Common Desktop Environment (CDE) and X Windows systems, which are common on commercial versions of Unix such as Solaris and IBM's AIX system. In addition, there has been significant development in GUI designs from various open-source projects such as K-Desktop Environment or KDE and the GNOME Desktop by the GNU project. Both the KDE and the GNOME desktops run on Linux and various Unix systems and are available under open-source licenses, which means their source code is readily available for reading and for modification under specific license terms. Choice of interface. The choice of whether to use a command line or GUI interface is mostly one of personal preference. System administrators who manage computers and power users who have deep knowledge of a system frequently use the command line interface. For them, it is more efficient, giving them faster access to the activities they need to perform. Indeed, on some systems, only a subset of system functions is available via the GUI, leaving the less common tasks to those who are command line knowledgeable. Further, command line interfaces usually make repetitive tasks easier, in part because they have their own programmability. For example, if a frequent task requires a set of command line steps, those steps can be recorded into a file and that file can be run just like a program. The program is not compiled into executable code but rather is interpreted by the command line interface. These shell scripts are very common on systems that are command line oriented such as Unix and Linux. Storage hierarchy. The wide variety of storage systems can be organized in a hierarchy. Figure shows storage hierarchy according to speed and cost. The higher levels are expensive, but they are fast. As we move down the hierarchy, the cost per bit generally decreases, whereas the access time generally increases. This trade-off is reasonable. If a given storage system were both faster and less expensive than another, other properties being the same, then there would be no reason to use the slower, more expensive memory. In fact, many early storage devices, including paper tape or core memories, are relegated to museums now that magnetic tape and semiconductor memory have become faster and cheaper. The top 4 levels of memory in the figure above may be constructed using semiconductor memory. In addition to differing in speed and cost, the various storage systems are either volatile or non-volatile. As mentioned earlier, volatile storage loses its contents when the power to the device is removed. In the absence of expensive battery and generator backup systems, data must be written to non-volatile storage for safekeeping. In the hierarchy shown in the figure above, the storage systems above the solid-state disk are volatile, whereas those including the solid-state disk and below are non-volatile. Solid-state disks have several variants, but in general are faster than magnetic disks and are non-volatile. One type of solid-state disk stores data in a large DRAM array during normal operation, but also contains a hidden magnetic hard disk and a battery for backup power. If external power is interrupted, the solid-state disk's controller copies the data from RAM to the magnetic disk. When external power is restored, the controller copies the data back into RAM. Another form of solid-state disk is flash memory, which is popular in cameras and personal digital assistants (PDAs), in robots, and increasingly for storage on general-purpose computers. Flash memory is slower than DRAM but needs no power to retain its contents. Another form of non-volatile storage is NVRAM, which is DRAM with battery backup power. This memory can be as fast as DRAM and, as long as the battery lasts, is non-volatile. The design of a complete memory system must balance all the factors just discussed. It must use only as much expensive memory as necessary while providing as much inexpensive, non-volatile memory as possible. Caches can be installed to improve performance where a large disparity in access time or transfer rate exists between two components. Storage structure. The CPU can load instructions only from memory, so any programs to run must be stored there. General-purpose computers run most of their programs from rewritable memory called main memory, also called random access memory or RAM. Main memory commonly is implemented in a semiconductor technology called dynamic random access memory, DRAM. Computers use other forms of memory as well. We have already mentioned read-only memory, ROM, and electrically erasable programmable read-only memory, EEPROM, because ROM cannot be changed. Only static programs such as the Bootstrap program described earlier are stored there. The immutability of ROM is of use in game cartridges. EEPROM can be changed but cannot be changed frequently and so contains mostly static programs. For example, smartphones have EEPROM to store their factory-installed programs. All forms of memory provide an array of bytes. Each byte has its own address. Interaction is achieved through a sequence of load or store instructions to specific memory addresses. The load instruction moves a byte or word from main memory to an internal register within the CPU, whereas the store instruction moves the content of a register to main memory. Aside from explicit loads and stores, the CPU automatically loads instructions from main memory for execution. A typical instruction execution cycle, as executed on a system with a von Neumann architecture, first fetches an instruction from memory and stores that instruction in the instruction register. The instruction is then decoded and may cause operands to be fetched from memory and stored in some internal register. After the instruction on the operands has been executed, the result may be stored back in memory. Notice that the memory unit sees only a stream of memory addresses. It does not know how they are generated by the instruction counter, indexing, indirection, literal addresses or some other means, or what they are for, instructions or data. Accordingly, we can ignore how a memory addresses is generated by a program. We are interested only in the sequence of memory addresses generated by the running program. Ideally, we want the programs and data to reside in main memory permanently. This arrangement usually is not possible for the following two reasons. 1. Main memory is usually too small to store all needed programs and data permanently. 2. Main memory is a volatile storage device that loses its contents when power is turned off or otherwise lost. Thus, most computer systems provide secondary storage as an extension of main memory. The main requirement for secondary storage is that it be able to hold large quantities of data permanently. The most common secondary storage device is a magnetic disk, which provides storage for both programs and data. Most programs, systems and applications are stored on a disk until they are loaded into memory. Many programs then use the disk as both the source and the destination of their processing. Hence, the proper management of disk storage is of central importance to a computer system. In a larger sense, however, the storage structure that we have described, consisting of registers, main memory, and magnetic disks, is only one of many possible storage systems. Others include cache memory, CD-ROM, magnetic tapes, and so on. Each storage system provides the basic functions of storing a datum and holding that datum until it is retrieved at a later time. The main differences among the various storage systems lie in speed, cost, size, and volatility. System calls. System calls provide an interface to the services made available by an operating system. These calls are generally available as routines written in C and C++, although certain low-level tasks, for example, tasks where hardware must be accessed directly, may have to be written using assembly language instructions. Before we discuss how an operating system makes system calls available, let's first use an example to illustrate how system calls are used, writing a simple program to read data from one file and copy them to another file. The first input that the program will need is the names of the two files, the input file and the output file. These names can be specified in many ways depending on the operating system design. One approach is for the program to ask the user for the names. In an interactive system, this approach will require a sequence of system calls, first to write a prompting message on the screen and then to read from the keyboard the characters that define the two files. On mouse-based and icon-based systems, a menu of file names is usually displayed in a window. The user can then use the mouse to select the source name, and a window can be opened for the destination name to be specified. The sequence requires many input-output system calls. Once the two file names have been obtained, the program must open the input file and create the output file. Each of these operations requires another system call. Possible error conditions for each operation can require additional system calls. When the program tries to open the input file, for example, it may find that there is no file of that name or that the file is protected against access. In these cases, the program should print a message on the console, another sequence of system calls, and then terminate abnormally another system call. If the input file exists, then we must create a new output file. We may find that there is already an output file with the same name. The situation may cause the program to abort a system call, or we may delete the existing file, another system call, and create a new one, yet another system call. Another option in an interactive system is to ask the user via a sequence of system calls to output the prompting message and to read the response from the terminal, whether to replace the existing file or to abort the program. When both files are set up, we enter a loop that reads from the input file a system call and writes to the output file another system call. Each read and write must return status information regarding various possible error conditions. On input, the program may find that the end of the file has been reached or that there was a hardware failure in the read, such as a parity error. The write operation may encounter various errors depending on the output device, for example, no more disk space. Finally, after the entire file is copied, the program may close both files, another system call, write a message to the console or window, more system calls, and finally terminate normally, the final system call. This system call sequence is shown in the figure below. As you can see, even simple programs may make heavy use of the operating system. Frequently, systems execute thousands of system calls per second. Most programmers never see this level of detail, however. Typically, application developers design programs according to an Application Programming Interface (API). The API specifies a set of functions that are available to an application programmer, including the parameters that are passed to each function and the return values of the programmer can expect. Three of the most common APIs available to application programmers are the Windows API for Windows systems, the POSIX API for POSIX-based systems, which include virtually all versions of Unix, Linux, and the Mac OS X, and the Java API for programs that run on the Java Virtual Machine. A programmer accesses an API via a library of code provided by the operating system. In the case of Unix and Linux, for programs written in the C language, the library is called libc. Note that, unless specified, the system call names used throughout this text are generic examples. Each operating system has its own name for each system call. Behind the scenes, the functions that make up an API typically invoke the actual system calls on behalf of the application programmer. For example, the Windows function createProcess function, which unsurprisingly is used to create a new process, actually invokes the ntCreateProcess function system call in the Windows kernel. Why would an application programmer prefer programming according to an API rather than invoking actual system calls? There are several reasons for doing so. One benefit concerns program portability. An application programmer designing a program using an API can expect her program to compile and run on any system that supports the same API, although, in reality, architectural differences often make this more difficult than it may appear. Furthermore, actual system calls can often be more detailed and difficult to work with than the API available to an application programmer. Nevertheless, there often exists a strong correlation between a function in the API and its associated system call within the kernel. In fact, many of the POSIX, POSIX, and Windows APIs are similar to the native system calls provided by the Unix, Linux, and Windows operating systems. For most programming languages, the runtime support system, a set of functions built into libraries included with a compiler, provides a system call interface that serves as the link to system calls made available by the operating system. The system call interface intercepts function calls in the API and invokes the necessary system calls within the operating system. Typically, a number is associated with each system call, and the system call interface maintains a table indexed according to these numbers. The system call interface then invokes the intended system call in the operating system kernel and returns the status of the system call and any return values. The caller need know nothing about how the system call is implemented or what it does during execution. Rather, the caller need only obey the API and understand what the operating system will do as a result of the execution of that system call. Thus, most of the details of the operating system interface are hidden from the programmer by the API and are managed by the runtime support library. The relationship between an API, the system call interface, and the operating system is shown in the figure below, which illustrates how the operating system handles a user application invoking the open function system call. System calls occur in different ways depending on the computer in use. Often, more information is required than simply the identity of the desired system call. The exact type and amount of information vary according to the particular operating system and call. For example, to get input, we may need to specify the file or device to use as the source, as well as the address and length of the memory buffer into which the input should be read. Of course, the device or file and length may be implicit in the call. Three general methods are used to pass parameters to the operating system. The simplest approach is to pass the parameters in registers. In some cases, however, there may be more parameters than registers. In these cases, the parameters are generally stored in a block or table in memory, and the address of the block is passed as a parameter in a register, as shown in the figure below. This is the approach taken by Linux and Solaris. Parameters also can be placed or pushed onto the stack by the program and popped off the stack by the operating system. Some operating systems prefer the block or stack method because those approaches do not limit the number or length of parameters being passed. Types of system calls. System calls can be grouped roughly into 6 major categories: process control, file manipulation, device manipulation, information maintenance, communications and protection. Most of these system calls support or are supported by concepts and functions. Process control: end, abort, load, execute, create process, terminate process, get process attributes, set process attributes, wait for time, wait event, signal event, allocate and free memory. File management: create file, delete file, open, close, read, write, reposition, get file attributes, set file attributes. Device management: request device, release device, read, write, reposition, get device attributes, set device attributes, logically attach or detach devices. Information maintenance: get time or date, set time or date, get system data, set system data, get process, file or device attributes, set process, file or device attributes. Communications: create, delete communication connection, send, receive messages, transfer status information, attach or detach remote devices. As mentioned in this text, we normally refer to the system calls by generic names. Throughout the text, however, we provide examples of the actual counterparts to the system calls for Windows, Unix, and Linux systems. Process control: a running program needs to be able to halt its execution either normally, end function, or abnormally, abort function. If a system call is made to terminate the currently running program abnormally, or if the program runs into a problem and causes an error trap, a dump of memory is sometimes taken and an error message generated. The dump is written to disk and may be examined by a debugger, a system program designed to aid the programmer in finding and correcting errors or bugs to determine the cause of the problem. Under either normal or abnormal circumstances, the operating system must transfer control to the invoking command interpreter. The command interpreter then reads the next command. In an interactive system, the command interpreter simply continues with the next command. It is assumed that the user will issue an appropriate command to respond to any error. In a GUI system, a pop-up window might alert the user to the error and ask for guidance. In a batch system, the command interpreter usually terminates the entire job and continues with the next job. Some systems may allow for special recovery actions in case an error occurs. If the program discovers an error in its input and wants to terminate abnormally, it may also want to define an error level. More severe errors can be indicated by a higher level error parameter. It is then possible to combine normal and abnormal termination by defining a normal termination as an error at level 0. The command interpreter or a following program can use this error level to determine the next action automatically. A process or job executing one program may want to load function and execute function another program. This feature allows the command interpreter to execute a program as directed by, for example, a user command, the click of a mouse, or a batch command. An interesting question is where to return control when the loaded program terminates. This question is related to whether the existing program is lost, saved, or allowed to continue execution concurrently with the new program. If control returns to the existing program when the new program terminates, we must save the memory image of the existing program. Thus, we have effectively created a mechanism for one program to call another program. If both programs continue concurrently, we have created a new job or process to be multi-programmed. Often, there is a system call specifically for this purpose, create process function or submit job function. If we create a new job or process, or perhaps even a set of jobs or processes, we should be able to control its execution. This control requires the ability to determine and reset the attributes of a job or process, including the job's priority, its maximum allowable execution time, and so on. Get process attributes function and set process attributes function. We may also want to terminate a job or process that we created, terminate process function, if we find that it is incorrect or is no longer needed. Having created new jobs or processes, we may need to wait for them to finish their execution. We may want to wait for a certain amount of time to pass, wait time function. Most probably, we will want to wait for a specific event to occur, wait event function. The jobs or processes should then signal when that event has occurred, signal event function. Quite often, two or more processes may share data. To ensure the integrity of the data being shared, operating systems often provide system calls allowing a process to lock shared data. Then, no other process can access the data until the lock is released. Typically, such system calls include acquire lock function and release lock function. System calls of these types dealing with the coordination of concurrent processes. There are so many facets of and variations in process and job control that we next use two examples, one involving a single tasking system and the other a multitasking system, to clarify these concepts. The MS-DOS operating system is an example of a single tasking system. It has a command interpreter that is invoked when the computer is started, as shown in figure A below. Because MS-DOS is single tasking, it uses a simple method to run a program and does not create a new process. It loads the program into memory, writing over most of itself to give the program as much memory as possible, as shown in figure B below. MS-DOS execution. A. At system startup. B. Running a program. Next, it sets the instruction pointer to the first instruction of the program. The program then runs and either an error causes a trap or the program executes a system call to terminate. In either case, the error code is saved in the system memory for later use. Following this action, the small portion of the command interpreter that was not overwritten resumes execution. Its first task is to reload the rest of the command interpreter from disk. Then the command interpreter make the previous error code available to the user or to the next program. FreeBSD, derived from Berkeley Unix, is an example of a multitasking system. When a user logs on to the system, the shell of the user's choice is run. This shell is similar to the MS-DOS shell in that it accepts commands and executes programs that the user requests. However, since FreeBSD is a multitasking system, the command interpreter may continue running while another program is executed, as shown in the FreeBSD running multiple programs. To start a new process, the shell executes a fork function system call. Then, the selected program is loaded into memory via an execute function system call and the program is executed. Depending on the way the command was issued, the shell then either waits for the process to finish or runs the process in the background. In the latter case, the shell immediately requests another command. When a process is running in the background, it cannot receive input directly from the keyboard because the shell is using this resource. Input-output is therefore done through files or through a GUI interface. Meanwhile, the user is free to ask the shell to run other programs, to monitor the progress of the running process, to change that program's priority, and so on. When the process is done, it executes an exit function system call to terminate, returning to the invoking process a status code of 0 or a non-zero error code. This status or error code is then available to the shell or other programs. File management. We can, however, identify several common system calls dealing with files. We first need to be able to create function and delete function files. Either system call requires the name of the file and perhaps some of the file's attributes. Once the file is created, we need to open function it and use it. We may also read function and write function or reposition function, rewind or skip to the end of the file, for example. Finally, we need to close function the file, indicating that we are no longer using it. We may need these same sets of operations for directories if we have a directory structure for organizing files in the file system. In addition, for either files or directories, we need to be able to determine the values of various attributes and perhaps to reset them if necessary. File attributes include the file name, file type, protection codes, accounting information, and so on. At least two system calls, get file attributes function and set file attributes function, are required for this function. Some operating systems provide many more calls, such as calls for file move function and copy function. Others might provide an API that performs those operations using code and other system calls, and others might provide system programs to perform those tasks. If the system programs are callable by other programs, then each can be considered an API by other system programs. Device management. A process may need several resources to execute: main memory, disk drives, access to files, and so on. If the resources are available, they can be granted and the control can be returned to the user process. Otherwise, the process will have to wait until sufficient resources are available. The various resources controlled by the operating system can be thought of as devices. Some of these devices are physical devices, for example, disk drives, while others can be thought of as abstract or virtual devices, for example, files. A system with multiple users may require us to first request function a device to ensure exclusive use of it. After we are finished with the device, we release function it. These functions are similar to the open function and close function system calls for files. Other operating systems allow unmanaged access to devices. The hazard, then, is the potential for device contention and perhaps deadlock. Once the device has been requested and allocated to us, we can read function, write function, and possibly reposition function the device just as we can with files. In fact, the similarity between input-output devices and the files is so great that many operating systems, including Unix, merge the two into a combined file-device structure. In this case, a set of system calls is used on both files and devices. Sometimes, input-output devices are identified by special file names, directory placement, or file attributes. The user interface can also make files and devices appear to be similar even though the underlying system calls are dissimilar. This is another example of the many design decisions that go into building an operating system and user interface. Information maintenance. Many system calls exist simply for the purpose of transferring information between the user program and the operating system. For example, most systems have a system call to return the current time function and date function. Other system calls may return information about the system, such as the number of current users, the version number of the operating system, the amount of free memory or disk space, and so on. Another set of system calls is helpful in debugging a program. Many systems provide system calls to dump function memory. This provision is useful for debugging. A program trace lists each system call as it is executed. Even microprocessors provide a CPU mode known as single step, in which a trap is executed by the CPU after every instruction. The trap is usually caught by a debugger. Many operating systems provide a time profile of a program to indicate the amount of time that the program executes at a particular location or set of locations. A time profile requires either a tracing facility or regular time interrupts. At every occurrence of the timer interrupt, the value of the program counter is recorded. With sufficiently frequent timer interrupts, a statistical picture of the time spent on various parts of the program can be obtained. In addition, the operating system keeps information about all its processes, and system calls are used to access this information. Generally, calls are also used to reset the process information, get process attributes function, and set process attributes function. Communication. There are two common models of interprocess communication: the message passing model and the shared memory model. In the message passing model, the communicating processes exchange messages with one another to transfer information. Messages can be exchanged between the processes either directly or indirectly through a common mailbox. Before communication can take place, a connection must be opened. The name of the other communicator must be known, be it another process on the same system or a process on another computer connected by a communications network. Each computer in a network has a host name by which it is commonly known. A host also has a network identifier such as an IP address. Similarly, each process has a process name, and this name is translated into an identifier by which the operating system can refer to the process. The getHostID function and getProcessID function system calls do this translation. The identifiers are then passed to the general purpose open function and close function calls provided by the file system, or to specific open connection function and close connection function system calls depending on the system's model of communication. The recipient process usually must give its permission for communication to take place with an accept connection function call. Most processes that will be receiving connections are special purpose daemons, which are system programs provided for that purpose. They execute a wait for connection function call and awaken when a connection is made. The source of the communication, known as the client, and the receiving daemon, known as a server, then exchange messages by using read message function and write message function system calls. The close connection function call terminates the communication. In the shared memory model, processes use shared memory create function and shared memory attach function system calls to create and gain access to regions of memory owned by other processes. Recall that normally the operating system tries to prevent one process from accessing another process's memory. Shared memory requires that two or more processes agree to remove this restriction. They can then exchange information by reading and writing data in the shared areas. The form of the data is determined by the processes and is not under the operating system's control. The processes are also responsible for ensuring that they are not writing to the same. Both of the models just discussed are common in operating systems, and most systems implement both. Message passing is useful for exchanging smaller amounts of data because no conflicts need be avoided. It is also easier to implement than is shared memory for intercomputer communication. Shared memory allows maximum speed and convenience of communication since it can be done at memory transfer speeds when it takes place within a computer. Problems exist, however, in the areas of protection and synchronization between the processes sharing memory. Protection. Protection provides a mechanism for controlling access to the resources provided by a computer system. Historically, protection was a concern only on multi-programmed computer systems with several users. However, with the advent of networking and the Internet, all computer systems, from servers to mobile handheld devices, must be concerned with protection. Typically, system calls providing protection include setPermission function and getPermission function, which manipulate the permission settings of resources such as files and disks. The AllowUser function and DenyUser function system calls specify whether particular users can or cannot be allowed access to certain resources. System components. Hardware provides basic computing resources, CPU, memory, input-output devices. Operating system controls and coordinates the use of the hardware among the various application programs for the various users. Applications programs define the ways in which the system resources are used to solve the computing problems of the users, compilers, database systems, video games, business programs. Users: people, machines, other computers. Abstract view of system components. System design and implementation. In this section, we discuss problems we face in designing and implementing an operating system. There are, of course, no complete solutions to such problems, but there are approaches that have proved successful. Design goals. The first problem in designing a system is to define goals and specifications. At the highest level, the design of the system will be affected by the choice of hardware and the type of system: batch, time-sharing, single-user, multi-user, distributed, real-time, or general purpose. Beyond this highest design level, the requirements may be much harder to specify. The requirements can, however, be divided into two basic groups: user goals and system goals. Users want certain obvious properties in a system. The system should be convenient to use, easy to learn and to use, reliable, safe, and fast. Of course, these specifications are not particularly useful in the system design, since there is no general agreement on how to achieve them. A similar set of requirements can be defined by those people who must design, create, maintain, and operate the system. The system should be easy to design, implement, and maintain. It should be flexible, reliable, error-free, and efficient. Again, these requirements are vague and may be interpreted in various ways. There is, in short, no unique solution to the problem of defining the requirements for an operating system. The wide range of systems in existence shows that different requirements can result in a large variety of solutions for different environments. For example, the requirements for VxWorks, a real-time operating system for embedded systems, must have been substantially different from those for MVS, a large multi-user, multi-access operating system for IBM mainframes. Specifying and designing an operating system is a highly creative task. Although no textbook can tell you how to do it, general principles have been developed in the field of software engineering, and we turn now to a discussion of some of these principles. One important principle is the separation of policy from mechanism. Mechanisms determine how to do something. Policies determine what will be done. For example, the timer construct is a mechanism for ensuring CPU protection, but deciding how long the timer is to be set for a particular user is a policy decision. The separation of policy and mechanism is important for flexibility. Policies are likely to change across places or over time. In the worst case, each change in policy would require a change in the underlying mechanism. A general mechanism insensitive to changes in policy would be more desirable. A change in policy would then require redefinition of only certain parameters of the system. For instance, consider a mechanism for giving priority to certain types of programs over others. If the mechanism is properly separated from policy, it can be used either to support a policy decision that input-output intensive programs should have priority over CPU intensive ones, or to support the opposite policy. Microkernel-based operating systems take the separation of mechanism and policy to one extreme by implementing a basic set of primitive building blocks. 3 blocks are almost policy-free, allowing more advanced mechanisms and policies to be added via user-created kernel modules or user programs themselves. As an example, consider the history of Unix. At first, it had a time-sharing scheduler. In the latest version of Solaris, scheduling is controlled by loadable tables. Depending on the table currently loaded, the system can be time-sharing, batch processing, real-time, fair share, or any combination. Making the scheduling mechanism general purpose allows vast policy changes to be made with a single load new table command. At the other extreme is a system such as Windows, in which both mechanism and policy are encoded in the system to enforce a global look and feel. All applications have similar interfaces because the interface itself is built into the kernel and system libraries. The Mac OS X operating system has similar functionality. Policy decisions are important for all resource allocation. Whenever it is necessary to decide whether or not to allocate a resource, a policy decision must be made. Whenever the question is how rather than what, it is a mechanism that must be determined. Implementation. Once an operating system is designed, it must be implemented because operating systems are collections of many programs written by many people over a long period of time. It is difficult to make general statements about how they are implemented. Early operating systems were written in assembly language. Now, although some operating systems are still written in assembly language, most are written in a higher level language such as C or an even higher level language such as C++. Actually, an operating system can be written in more than one language. The lowest levels of the kernel might be assembly language. Higher level routines might be in C, and system programs might be in C or C++ in interpreted scripting languages like Perl or Python, or in shell scripts. In fact, a given Linux distribution probably includes programs written in all of these languages. The first system that was not written in assembly language was probably the Master Control Program (MCP) for Burroughs computers. MCP was written in a variant of Algol. Multics, developed by MIT, was written mainly in the system programming language PL/1. The Linux and Windows operating system kernels are written mostly in C, although there are some small sections of assembly code for device drivers and for saving and restoring the state of registers. The advantages of using a higher level language, or at least a systems implementation language, for implementing operating systems are the same as those gained when the language is used for application programs. The code can be written faster, is more compact, and is easier to understand and debug. In addition, improvements in compiler technology will improve the generated code for the entire operating system by simple recompilation. Finally, an operating system is far easier to port to move to some other hardware if it is written in a higher level language. For example, MS-DOS was written in Intel 8088 assembly language. Consequently, it runs natively only on the Intel x86 family of CPUs. Note that although MS-DOS runs natively only on Intel x86, emulators of the x86 instruction set allow the operating system to run on other CPUs, but more slowly and with higher resource use. As we mentioned, emulators are programs that duplicate the functionality of one system on another system. The Linux operating system, in contrast, is written mostly in C and is available natively on a number of different CPUs, including Intel x86, Oracle SPARC, and IBM PowerPC. The only possible disadvantages of implementing an operating system is a higher level language are reduced speed and increased storage requirements. This, however, is no longer a major issue in today's systems. Although an expert assembly language programmer can produce efficient small routines, for large programs, a modern compiler can perform complex analysis and apply sophisticated optimizations that produce excellent code. Modern processors have deep pipelining and multiple functional units that can handle the details of complex dependencies much more easily than can the human mind. As is true in other systems, major performance improvements in operating systems are more likely to be the result of better data structures and algorithms than of excellent assembly language code. In addition, although operating systems are large, only a small amount of the code is critical to high performance. The interrupt handler, input-output manager, memory manager, and CPU scheduler are probably the most critical routines. After the system is written and is working correctly, Bottleneck routines can be identified and can be replaced with assembly language equivalents. System generation. It is possible to design, code, and implement an operating system specifically for one machine at one site. More commonly, however, operating systems are designed to run on any of a class of machines at a variety of sites with a variety of peripheral configurations. The system must then be configured or generated for each specific computer site, a process sometimes known as system generation, sysgen. The operating system is normally distributed on disk, on CD-ROM or DVD-ROM, or as an ISO image, which is a file in the format of a CD-ROM or DVD-ROM. To generate a system, we use a special program. This sysgen program reads from a given file or asks the operator of the system for information concerning the specific configuration of the hardware system, or probes the hardware directly to determine what components are there. The following kinds of information must be determined: what CPU is to be used, what options, extended instruction sets, floating point arithmetic, and so on are installed. For multiple CPU systems, each CPU may be described. How will the boot disk be formatted? How many sections or partitions will it be separated into, and what will go into each partition? How much memory is available? Some systems will determine this value themselves by referencing memory location after memory location until an illegal address fault is generated. This procedure defines the final legal address and hence the amount of available memory. What devices are available? The system will need to know how to address each device, the device number, the device interrupt number, the device's type and model, and any special device characteristics. What operating system options are desired, or what parameter values are to be used? These options or values might include how many buffers of which sizes should be used, what type of CPU scheduling algorithm is desired, what the maximum number of processes to be supported is, and so on. Once this information is determined, it can be used in several ways. At one extreme, a system administrator can use it to modify a copy of the source code of the operating system. The operating system then is completely compiled. Data declarations, initializations, and constants, along with conditional compilation, produce an output object version of the operating system that is tailored to the system described. At a slightly less tailored level, the system description can lead to the creation of tables and the selection of modules from a pre-compiled library. These modules are linked together to form the generated operating system. Selection allows the library to contain the device drivers for all supported input-output devices, but only those needed are linked into the operating system because the system is not recompiled. System generation is faster, but the resulting system may be overly general. At the other extreme, it is possible to construct a system that is completely table-driven. All the code is always part of the system and selection occurs at execution time rather than at compile or link time. System generation involves simply creating the appropriate tables to describe the system. The major differences among these approaches are the size and generality of the generated system and the ease of modifying it as the hardware configuration changes. Consider the cost of modifying the system to support a newly acquired graphics terminal or another disk drive. Balanced against that cost, of course, is the frequency or infrequency of such changes. System programs. System programs. Another aspect of a modern system is its collection of system programs. Recall figure below, which depicted the logical computer hierarchy. At the lowest level is hardware. Next is the operating system, then the system programs, and finally the application programs. System programs, also known as system utilities, provide a convenient environment for program development and execution. Some of them can simply use interfaces to system calls. Others are considerably more complex. They can be divided into these categories. File management. These programs create, delete, copy, rename, print, dump, list, and generally manipulate files and directories. Status information. Some programs simply ask the system for the date, time, amount of available memory or disk space, number of users, or similar status information. Others are more complex, providing detailed performance, logging, and debugging information. Typically, these programs format and print the output to the terminal or other output devices or files, or display it in a window of the GUI. Some systems also support a registry, which is used to store and retrieve configuration information. File modification. Several text editors may be available to create and modify the content of files stored on disk or other storage devices. There may also be special commands to search contents of files or perform transformations of the text. Programming language support. Compilers, assemblers, debuggers, and interpreters for common programming languages such as C, C++, Java, and Perl are often provided with the operating system or available as a separate download. Program loading and execution. Once a program is assembled or compiled, it must be loaded into memory to be executed. The system may provide absolute loaders, relocatable loaders, linkage editors, and overlay loaders. Debugging systems for either higher-level languages or machine language are needed as well. Communications. These programs provide the mechanism for creating virtual connections among processes, users, and computer systems. They allow users to send messages to one another's screens, to browse web pages, to send email messages, to log in remotely, or to transfer files from one machine to another. Background services. All general-purpose systems have methods for launching certain system program processes at boot time. Some of these processes terminate after completing their tasks, while others continue to run until the system is halted. Constantly running system program processes are known as services, subsystems, or daemons. In that example, a system needed a service to listen for network connections in order to connect those requests to the correct processes. Other examples include process schedulers that start processes according to a specified schedule, system error monitoring services, and print servers. Typical systems have dozens of daemons. In addition, operating systems that run important activities in user context rather than in kernel context may use daemons to run these activities. Along with system programs, most operating systems are supplied with the programs that are useful in solving common problems or performing common operations. Such application programs include web browsers, word processors, and text formaters, spreadsheets, database systems, compilers, plotting and statistical analysis packages, and games. The view of the operating system seen by most users is defined by the application and system programs rather than by the actual system calls. Consider a user's PC. When a user's computer is running the Mac OS X operating system, the user might see the GUI featuring a mouse and Windows interface. Alternatively, or even in one of the windows, the user might have a command line Unix shell. Both use the same set of system calls, but the system calls look different and act in different ways. Further confusing the user view, consider the user dual booting from Mac OS X into Windows. Now, the same user on the same hardware has two entirely different interfaces and two sets of applications using the same physical resources. On the same hardware, then, a user can be exposed to multiple user interfaces sequentially or concurrently. System structure. A system as large and complex as a modern operating system must be engineered carefully if it is to function properly and be modified easily. A common approach is to partition the task into small components or modules rather than have one monolithic system. Each of these modules should be a well-defined portion of the system with carefully defined inputs, outputs, and functions. In this section, we discuss how these general system components are interconnected and melded into a kernel. Simple structure. Many operating systems do not have well-defined structures. Frequently, such systems started as small, simple and limited systems and then grew beyond their original scope. MS-DOS is an example of such a system. It was originally designed and implemented by a few people who had no idea that it would become so popular. It was written to provide the most functionality in the least space, so it was not carefully divided into modules. The figure below shows MS-DOS structure. In MS-DOS, the interfaces and levels of functionality are not well separated. For instance, application programs are able to access the basic input-output routines to write directly to the display and disk drives. Such freedom leaves MS-DOS vulnerable to errant or malicious programs, causing entire system crashes when user programs fail. Of course, MS-DOS was usually limited by the hardware of its era. Because the Intel 8088 for which it was written provides no dual mode and no hardware protection, the designers of MS-DOS had no choice but to leave the base hardware accessible. Another example of limited structuring is the original Unix operating system. Like MS-DOS, Unix initially was limited by hardware functionality. It consists of two separate parts, the kernel and the system programs. The kernel is further separated into a series of interfaces and device drivers which have been added and expanded over the years as Unix has evolved. We can view the traditional Unix operating system as being layered to some extent as shown in the figure below. Everything below the system call interface and above the physical hardware is the kernel. The kernel provides the file system, CPU scheduling, memory management, and other operating system functions through system calls. Taken in sum, that is an enormous amount of functionality to be combined into one level. The monolithic structure was difficult to implement and maintain. It had a distinct performance advantage, however. There is very little overhead in the system call interface or in communication within the kernel. We still see evidence of this simple monolithic structure in the Unix, Linux, and Windows operating systems. Layered approach. With proper hardware support, operating systems can be broken into pieces that are smaller and more appropriate than those allowed by the original MS-DOS and Unix systems. The operating system can then retain much greater control over the computer and over the applications that make use of that computer. Implementers have more freedom in changing the inner workings of the system and in creating a modular operating systems. Under a top-down approach, the overall functionality and features are determined and are separated into components. Information hiding is also important because it leaves programmers free to implement the low-level routines as they see fit, provided that the external interface of the routine stays unchanged and that the routine itself performs the advertised task. A system can be made modular in many ways. One method is the layered approach, in which the operating system is broken into a number of levels. The bottom layer, level 0, is the hardware. The highest, layer N, is the user interface. This layering structure is depicted in the figure below. An operating system layer is an implementation of an abstract object made up of data and the operations that can manipulate those data. A typical operating system layer, say layer M, consists of data structures and a set of routines that can be invoked by higher level layers. Layer M, in turn, can invoke operations on lower level layers. The main advantage of the layered approach is simplicity of construction and debugging. The layers are selected so that each uses functions, operations, and services of only lower-level layers. This approach simplifies debugging and system verification. The first layer can be debugged without any concern for the rest of the system because, by definition, it uses only the basic hardware which is assumed correct to implement its functions. Once the first layer is debugged, its correct functioning can be assumed while the second layer is debugged, and so on. If an error is found during the debugging of a particular layer, the error must be on that layer because the layers below it are already debugged. Thus, the design and implementation of the system are simplified. Each layer is implemented only with the operations provided by lower-level layers. A layer does not need to know how these operations are implemented. It needs to know only what these operations do. Hence, each layer hides the existence of certain data structures, operations, and hardware from higher-level layers. The major difficulty with the layered approach involves appropriately defining the various layers. Because a layer can use only lower-level layers, careful planning is necessary. For example, the device driver for the backing store, disk space used by virtual memory algorithms, must be at a lower level than the memory management routines because memory management requires the ability to use the backing store. Other requirements may not be so obvious. The backing store driver would normally be above the CPU scheduler because the driver may need to wait for input-output and the CPU can be rescheduled during this time. However, on a large system, the CPU scheduler may have more information about all the active processes than can fit in memory. Therefore, this information may need to be swapped in and out of memory, requiring the backing store driver routine to be below the CPU scheduler. A final problem with layered implementations is that they tend to be less efficient than other types. For instance, when a user program executes an input-output operation, it executes a system call that is trapped to the input-output layer, which calls the memory management layer, which in turn calls the CPU scheduling layer, which is then passed to the hardware. At each layer, the parameters may be modified, data may need to be passed, and so on. Each layer adds overhead to the system call. The net result is a system call that takes longer than does one on a non-layered system. These limitations have caused a small backlash against layering in recent years. Fewer layers with more functionality are being designed, providing most of the advantages of modularized code while avoiding the problems of layer definition and interaction. Microkernels. We have already seen that as Unix expanded, the kernel became large and difficult to manage. In the mid-1980s, researchers at Carnegie Mellon University developed an operating system called MASH that modularized the kernel using the microkernel approach. This method structures the operating system by removing all non-essential components from the kernel and implementing them as system and user-level programs. The result is a smaller kernel. There is little consensus regarding which services should remain in the kernel and which should be implemented in user space. Typically, however, microkernels provide minimal process and memory management in addition to a communication facility. Figure below illustrates the architecture of a typical microkernel. The main function of the microkernel is to provide communication between the client program and the various services that are also running in user space. Communication is provided through message passing. For example, if the client program wishes to access a file, it directly. Rather, they communicate indirectly by exchanging messages with the microkernel. One benefit of the microkernel approach is that it makes extending the operating system easier. All new services are added to user space and consequently do not require modification on the kernel. When the kernel does not have to be modified, the changes tend to be fewer because the microkernel is a smaller kernel. The resulting operation system is easier to port from one hardware design to another. The microkernel also provides more security and reliability since most services are running as user rather than kernel processes. If a service fails, the rest of the operating system remains untouched. Some contemporary operating systems have used the microkernel approach. Tru64 Unix, formerly Digital Unix, provides a Unix interface to the user, but it is implemented with a MASH kernel. The MAC kernel maps Unix system calls into messages to the appropriate user-level services. The Mac OS X kernel, also known as Darwin, is also partly based on the MASH microkernel. Another example of QNX, a real-time operating system for embedded systems. The QNX Neutrino microkernel provides services for message passing and process scheduling. It also handles low-level network communication and hardware interrupts. All other services in QNX are provided by standard processes that run outside the kernel in user mode. Unfortunately, the performance of microkernels can suffer due to increased system function overhead. Consider the history of Windows NT. The first release had a layered microkernel organization. This version's performance was low compared with that of Windows 95. Windows NT 4.0 partially corrected the performance problem by moving layers from user space to kernel space and integrating them more closely. By the time Windows XP was designed, Windows architecture had become more monolithic than microkernel. Modules. Perhaps the best current methodology for operating system design involves using loadable kernel modules. Here, the kernel has a set of core components and links in additional services via modules, either at boot time or during runtime. This type of design is common in modern implementations of Unix, such as Solaris, Linux, and Mac OS X, as well as Windows. The idea of the design is for the kernel to provide core services while other services are implemented dynamically as the kernel is running. Linking services dynamically is preferable to adding new features directly to the kernel, which would require recompiling the kernel every time a change was made. Thus, for example, we might build CPU scheduling and memory management algorithms directly into the kernel and then add support for different file systems by way of loadable modules. The overall result resembles a layered system in that each kernel section has defined, protected interfaces, but it is more flexible than a layered system because any module can call any other module. The approach is similar to the microkernel approach in that the primary module has only core functions and knowledge of how to load and communicate with other modules, but It is more efficient because modules do not need to invoke message passing in order to communicate. The Solaris operating system structure shown in the figure below is organized around a core kernel with 7 types of loadable kernel modules. 1. Scheduling classes. 2. File systems. 3. Loadable system calls. 4. Executable formats. 5. Streams modules. 6. Miscellaneous. 7. Device and bus drivers. Linux also uses loadable kernel modules primarily for supporting device drivers and file systems. Hybrid systems. In practice, very few operating systems adopt a single, strictly defined structure. Instead, they combine different structures, resulting in hybrid systems that address performance, security, and usability issues. For example, both Linux and Solaris are monolithic because having the operating system in a single address space provides very efficient performance. However, they are also modular so that new functionality can be dynamically added to the kernel. Windows is largely monolithic as well, again primarily for performance reasons, but it retains some behavior typical of microkernel systems, including providing support for separate subsystems known as operating system personalities that run as user mode processes. Windows systems also provide support for dynamically loadable kernel modules. In the remainder of this section, we explore the structure of 3 hybrid systems, the Apple Mac OS X operating system and the 2 most prominent mobile operating systems, iOS and Android. Mac OS X. The Mac OS X operating system uses a hybrid structure. As shown above, it is a layered system. The top layers include the Aqua user interface, figure below, and a set of application environments and services. Notably, the Cocoa environment specifies an API for the Objective-C programming language, which is used for writing Mac OS X applications. Below these layers is the kernel environment, which consists primarily of the Match microkernel and the BSD Unix kernel. The Match provides memory management, support for remote procedure calls RPCs, and interprocess communication IPC facilities, including message passing and thread scheduling. The BSD component provides a BSD command line interface, support for networking and file systems, and an implementation of POSIX APIs, including pthreads. In addition to MASH and BSD, the kernel environment provides an input-output kit for the development of device drivers and dynamically loadable modules, which Mac OS X refers to as kernel extensions. As shown in the figure below, the BSD application environment can make use of BSD facilities directly. iOS. iOS is a mobile operating system designed by Apple to run its smartphone, the iPhone, as well as its tablet computer, the iPad. iOS is structured on the Mac OS X operating system, which added functionality pertinent to the mobile devices but does not directly run Mac OS X applications. The structure of iOS appears in the figure below. Cocoa Touch is an API for Objective-C that provides several frameworks for developing applications that run on iOS devices. Fundamental differences between Cocoa, mentioned earlier, and Cocoa Touch is that the latter provides support for hardware features unique to mobile devices such as touchscreens. The media services layer provides services for graphics, audio, and video. The core services layer provides a variety of features, including support for cloud computing and databases. The bottom layer represents the core operating system, which is based on the kernel environment shown in figure below. Android. The Android operating system was designed by the Open Handset Alliance, led primarily by Google, and was developed by Android smartphones and tablet computers. Whereas iOS is designed to run on Apple mobile devices and is closed-sourced, Android runs on a variety of mobile platforms and is open-sourced, partly explaining its rapid rise in popularity. The structure of Android appears in figure below. Android is similar to iOS in that it is a layered stack of software that provides a rich set of frameworks for developing mobile applications. At the bottom of this software stack is the Linux kernel, although it has been modified by Google and is currently outside the normal distribution of Linux releases. Linux is used primarily for process, memory and device driver support for hardware and has been expanded to include power management. The Android environment includes a core set of libraries as well as the Dalvik virtual machine. Software designers for Android devices develop applications in the Java language. However, rather than using the standard Java API, Google has designed a separate Android API for Java development. The Java class files are first compiled to Java bytecode and then translated into an executable file that runs on the Dalvik virtual machine. The Dalvik virtual machine was designed for Android and is optimized for mobile devices with limited memory and CPU processing capabilities. The set of libraries available for Android applications includes frameworks for developing web browsers, WebKit, database support, SQLite, and multimedia. The libc library is similar to the standard C library but is much smaller and has been designed for the slower CPUs that characterize mobile devices. Time-sharing system. A time-sharing system uses CPU scheduling and multi-programming to provide each user with a small portion of a time-shared computer. The CPU is multiplexed among several jobs that are kept in memory and on disk. The CPU is allocated to a job only if the job is in memory. When a job needs an I/O operation, the CPU switches between jobs. Therefore, the CPU is always busy. A job is swapped in and out of memory to the disk, which serves as a backup for main memory. Online communication between the user and the system is provided. When the operating system finishes the execution of one command, it seeks the next control statement not from a card reader but rather from the user's keyboard. Online system must be available for users to access data and code. A time-sharing system uses CPU scheduling and multi-programming to provide each user with a small portion of a time-shared computer. As shown, multi-programming memory management. As shown, time-sharing systems provide the following. Online file system, where the files are on a collection of disks, therefore disk management must be provided. A mechanism for concurrent execution, which requires CPU scheduling schemes. Mechanisms for job synchronization and communication to ensure orderly execution. A mechanism to avoid deadlock, a job waiting for another job forever. Advantages of time-sharing operating systems are following. Provide advantage of quick response, avoids duplication of software, reduces CPU idle time. Disadvantages of time-sharing operating systems are following. Problem of reliability, question of security and integrity of user programs and data, problem of data communication. Virtual machines and hypervisor. Virtualization technology enables a single PC or server to simultaneously run multiple operating systems or multiple sessions of a single OS. A machine with virtualization software can host numerous applications, including those that run on different operating systems on a single platform. A virtual machine, VM, is an efficient, isolated duplicate of a real machine. Duplicate. VM should behave identically to the real machine. Programs cannot distinguish between execution on real or virtual hardware except for less resources available and potentially different between executions, some timing differences when dealing with devices. Isolated. Several VMSs execute without interfering with each other. Efficient. VM should execute at a speed close to that of hardware. Requires that most instructions are executed directly by real hardware. The host operating system can support a number of virtual machines, each of which has the characteristics of a particular OS. The solution that enables virtualization is a virtual machine monitor, VMM, or hypervisor. Types of virtual machines. Contemporary use of the term VM is more general. Call virtual machines even if there is no correspondence to an existing real machine. Example, Java Virtual Machine can be viewed as virtualizing at the ABI level, also called Process VM. We only concern ourselves with virtualizing at the ISA level. ISA, Instruction Set Architecture, Hardware-Software Interface, also called System VM. We'll later see subclasses of this. Virtual Machine Monitor, VMM, or Hypervisor. Program that runs on real hardware to implement the control resources, partitions hardware, schedules guests, mediates access to shared resources, devices, console, performs world switch. Implications. Hypervisor executes in privileged mode. Guest software executes in unprivileged mode. Privileged instructions in guest cause a trap into hypervisor. Hypervisor interprets, emulates them. Can have extra instructions for hypercalls. Invocation of hypervisor APIs that are not machine instructions. Web services. Web services are open standard XML, SOAP, HTTP, etc. based web applications that interact with other web applications for the purpose of exchanging data. Web services can convert your existing applications into web applications. A web service is any piece of software that makes itself available over the internet and uses a standardized XML messaging system. XML is used to encode all communications to a web service. For example, a client invokes a web service by sending an XML message, then waits for a corresponding XML response. As all communication is in XML, web services are not tied to any one operating system or programming language. Java can talk with Perl. Windows applications can talk with Unix applications. Web services are self-contained, modular, distributed, dynamic applications that can be described, published, located, or invoked over the network to create products, processes, and supply chains. These applications can be local, distributed, or web-based. Web services are built on top of open standards such as TCP over IP, HTTP, Java, HTML, and XML. Web services are XML-based information exchange systems that use the Internet for direct application-to-application interaction. These systems can include programs, objects, messages, or documents. A web service is a collection of open protocols and standards used for exchanging data between applications or systems. Software applications written in various programming languages and running on various platforms can use web services to exchange data over computer networks like the Internet in a manner similar to inter-process communication on a single computer. This interoperability, example between Java and Python or Windows and Linux applications, is due to the use of open standards. The basic web services platform is XML plus HTTP. All the standard web services work using the following components: SOAP, Simple Object Access Protocol; UDDI, Universal Description, Discovery and Integration; WSDL, Web Services Description Language. How does a web service work? A web service enables communication among various applications by using open standards such as HTML, XML, WSDL, and SOAP. A web service takes the help of XML to tag the data, SOAP to transfer a message, WSDL to describe the availability of service. You can build a Java-based web service on Solaris that is accessible from your Visual Basic program that runs on Windows. You can also use CHash to build new web services on Windows that can be invoked from your web application that is based on Java Server Pages, JSP, and runs on Linux. Here are the benefits of using web services. Exposing the existing function on the network. A web service is a unit of managed code that can be remotely invoked using HTTP. That is, it can be activated using HTTP requests. Web services allow you to expose the functionality of your existing code over the network. Once it is exposed on the network, other applications can use the functionality of your program. Interoperability. Web services allow various applications to talk to each other and share data and services among themselves. Other applications can also use the web services. For example, a VB or .NET application can talk to Java web services and vice versa. Web services are used to make the application platform and technology independent. Standardized protocol. Web services use standardized industry standard protocol for communication. All the four layers, service transport, XML messaging, service description, and service discovery layers, use well-defined protocols in the web services protocol stack. This standardization of protocol stack gives the business many advantages such as a wide range of choices, reduction in the cost due to competition, and increase in the quality. Low-cost communication. Web services use SOAP over HTTP protocol, so you can use your existing low-cost internet for implementing web services. This solution is much less costly compared to proprietary solutions like EDI/B2B. Besides SOAP over HTTP, web services can also be implemented on other reliable transport mechanisms like FTP. Conclusion. In this chapter, we have covered the following in detail: Introduction, Operating Systems, Multi-programmed Batch System, Time Storing Systems, Parallel and Distributed Systems, Real-Time Systems. Computer system structures: input-output structure, storage hierarchy, hardware, protection, general system structure. Services: user interface services, graphics and multimedia services, messaging and collaboration, network basics, web services. Operating system structures: system components, operating system service, system calls, system programs, system structure, system design and implementation, system generation, virtual machines, and hypervisor.